Hello, welcome to Math 253, Calculus 3 here at Cañada College. My name is Lapuz. In this video, we are starting section 6.4 with our checkpoints. This is checkpoint 6.34. I want us to use Green's theorem to calculate the line integral. This line integral over c of sine x squared dx plus 3x minus y dy, where C is a right triangle with vertices at negative 1, 2, 4, 2, and 4, 5, oriented in a counterclockwise direction. Let's figure out how that looks like. Negative 1, 2 would probably be somewhere over here in the third quadrant. We're going to go to 4, 2 in the first quadrant, and then we go up to 5, 2, and back down again. And they give us an orientation, which is going in a counterclockwise direction. And this is actually a very nice setup for Green's theorem, because instead of doing C1, C2, and C3, 3 line integrals, which is what we would have to do if we were to do this directly, we can simply use Green's theorem. Now, what is Green's theorem? Green's theorem tells us that we can replace this line integral, and notice that there's a loop in your integral sign, and that circle around the integral sign says that this is a closed curve. We have the sine of x squared dx plus 3, let me do this generically or generally. And Green's theorem says the line integral over a closed curve C of p dx plus q dy will equal to a double integral over d, and the relationship between c and d is that c, the curve, the closed curve, is the boundary of your domain D. And here we have the partial of q with respect to x minus the partial of p with respect to y dA. So this is a double integral. dA would represent dx dy unless we switch coordinate systems. So now that we have that, we can identify a few things. First, we should identify that the domain D that we're talking about is this region over here. And if you were to describe the domain D to prep it for your double integral, I would probably want to, well, you could do this as a type 1 or type 2 region, but I would probably treat this as a type 1 region to say that we're going to enter through with y limits from 0 to the equation of this line. So the equation of this line looks like it has a slope this should be 4, 2, and this should be 4, 5, sorry. And so the slope is the rise over run, and so that has a rise of 3 and a run of 5, 3/5, x minus -1, and the y value at that point is 2. All right, so this is your equation of this line. Y is equal to 3/5 x plus 1 times x, 3/5 times x plus 1 plus 2. And then our x limits would be constants going from -1 to 4. All right, so we can use that as our integral once we get it set up. The other thing that we need would be some partial derivatives. We'll identify p to be sine x squared. P is sine x squared, and then q is 3x minus y. And given that, we want the derivative of q with respect to x, and so that's going to be 3, and then we want the derivative of p with respect to y. There are no y's in there, so that's going to be 0. So this turns out to be an even nicer integral. So we can say that our line integral of sine x squared dx plus 3x minus y dy will actually equal to the double integral over this domain D of 3 minus 0 dA. All right. Now that we're seeing this as a constant, let us use another fact that we learned when we were learning double integrals, and that is if we take this 3 out, we have the integral of d of 1 dA. Do we remember that the integral, the double integral of d over d of the function 1 dA is simply equal to the area of d? So 3 times area of d. So we don't really even have to do an integral here. We just have to find the area. I think we found the area when we were doing the rise over run. The base looks like it's going to be 5, and then the height looks like it's going to be 3. And this is a triangle, so we have a 3 times 1/2 base times height. So we have 15 and 3 is 45, 45 over 2, and that should be our final answer. That's 45 over 2 is your final answer. All right. Okay, I hope that helps.